Isomorphism. The content of this topic are definition and understanding isomorphism, examples and non-examples of isomorphism, Thales' theorem, and the properties of isomorphism. Isomorphism. The word derives from the Greek iso, meaning equal, and morphosis, meaning to form or to shape. In the same way, isomorphic groups are grouped with the same form, iso plus morph. Now let's see these two figures. We have here the dihedral figure, which is the D4, and the Thales diagram. Using Thales diagram, we will find the rotation and reflection of our dihedral figure, which is the D4. Therefore, the elements of D4 is equal to E R squared R cubed F R squared F and R cubed F. Now let's find the permutation groups of rotations and reflections. So first, let's find the rotation. E is equal to the identity. Therefore, our group is 1, 2, 3, and 4. Next are 90 degrees rotation. So we will rotate. 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. Next are squared 180 degrees. Therefore, our permutation groups are 1 goes to 3 and 2 goes to 4. Next, R cube, which is 270 degrees. Therefore, our permutation groups is R. 1 goes to 4, then 4 goes to 3, then 3 goes to 2. Now, let's find the permutation groups of reflection. First, let's draw a diagonal line. So, our F is equal to 2 goes to 4. Next, our F. Rotate 90 degrees, then flip 1 and 3. Therefore, our groups are 1 goes to 4 and 2 goes to 3. Next, R squared F. Rotate 180 degrees, then flip 4 and 2. Therefore, our group is 1 goes to 3. Next, R cube F. Rotate 270 degrees, then flip 3 and 1. Therefore, our groups are 1 goes to 2 and 3 goes to 4. Substituting our permutation groups to Thales diagram, now we have two identical diagrams with different label. E maps 1, 2, 3, and 4. R maps 1 goes to 2, 2 goes to 3, and 3 goes to 4. R squared maps 1 goes to 3 and 2 goes to 4. R cube maps 1 goes to 4, 4 goes to 3, and 3 goes to 2. F maps 2 goes to 4. RF maps 1 goes to 4 and 2 goes to 3. R squared F maps 1 goes to 3, and R cube F maps 1 goes to 2 and 3 goes to 4. Next, definition of isomorphism. An isomorphism phi from a group G to a group G bar is a one-to-one function from G to G bar that preserves the group operation, or that phi of AB is equal to phi of A, phi of B. Keep in mind that on the left, we use the group operation for G and on the right for G bar. To prove a mapping is an isomorphism, we must show four properties hold. First, mapping. The mapping is simply the function that maps element of G to elements of G bar. If your groups are finite and small in size, it is easy to define a mapping by listing which elements of G map to which elements of G bar. If the groups are infinite, the mapping is generally a mathematical function. Second, one-to-one. Assume that phi of A is equal to phi of B and prove that A is equal to B. Third, onto. For every element, G bar is an element G bar, find an element G is an element of G, such that phi of G is equal to G bar. Fourth, operation preserving show that phi of AB is equal to phi of A, phi of B, or phi of AB is equal to phi of A plus phi of B, or phi of A plus B is equal to phi of A, phi of B, or phi of A plus B is equal to phi of A plus phi of B. For example, let's prove that D sub 4 is isomorphic to the subgroup of G of S sub 4, such that G is equal to 1, 2, 3, 4, 1, 3, 2, 4, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, 1, 2, 3, 4, and 1, 4, 3, 2. First, mapping. In this case, we can use our Cayley diagrams to represent the mapping of our function phi from D sub 4 to G. We can also state that phi of R is equal to 1, 2, 3, 4, and phi of F is equal to 2, 4. Next, 1 to 1. Using the Cayley diagram, which shows that for every phi of A is equal to phi of B, it must be true that A is equal to B. Example, 1, 2, 3, 4. We know that phi of R is equal to 1, 2, 3, 4, and 1, 2, 3, 4 is equal to phi of R. 1, 2, 3, 4 is equal to 1, 2, 3, 4, then R is equal to R. Onto. Again, we can cheat using our Cayley diagram. It is clear that for every element G is an element G, we can find an element D is an element D4, such that phi of D is equal to G. Next, operation preserving. We cheat again because we have well defined our mapping from the start. It is clear that phi of AB is equal to phi of A, phi of B. For example, phi of RF is equal to 1, 4, 2, 3. Is equal to 1, 2, 3, 4, 2, 4 is equal to phi of R, phi of F. Now let's move to the examples and non-examples of isomorphism. Let G is equal to Z plus and G bar is equal to 2Z plus prove that G is isomorphic to G bar. First mapping, define phi of X equal to 2X for all X is an element of G, which is true. Second, 1 to 1, phi of X equal to phi of Y. Show that X is equal to Y. Let 2X equals to Y by division, X is equal to Y. Third, onto, for each Y is an element of G bar, there exists X is an element of G, such that phi of X equal to Y. Y equals 2X, so X is equal to Y all over 2, and X is an element of Z, which is true. Fourth, operation preserving, phi of M plus N is equal to phi of M plus phi of N. 2, the quantity M plus N is equal to 2M plus 2N is equal to phi of M plus phi of N, which is true. Let G is equal to R plus and G bar is equal to R plus prove that G is isomorphic to G bar under phi of X is equal to X cubed. First, mapping, define let phi of X is equal to X cubed. Second, 1 to 1. Phi of X is equal to phi of Y, then X is equal to Y. X cubed is equal to Y cubed, then get the cube root of X and the cube root of Y, then X is equal to Y. Third, onto, Y is equal to X cubed, then the cube root of Y is equal to X. X is an element of G. Fourth, operation preserving. Phi of X plus Y is equal to phi of X plus phi of Y. X plus Y, the quantity cube, is not equal to X cubed plus Y cubed. Let G equals U10 and G bar equals U5 prove that G is isomorphic to G bar. First, get the order of each element of G and G bar. U10 is equal to 1, 3, 7, 9. Generator 1 is equal to 1 element. Order of 1 is equal to 1. Generator 3 has 4 elements, therefore the order of 3 is equal to 4. Generator 7 has 4 elements, therefore the order of 7 is equal to 4. Generator 9 has 2 elements, therefore the order of 9 is equal to 2. Next, U5 is equal to 1, 2, 3, 4. Generator 1 is equal to 1 element, therefore order of 1 is equal to 1. Generator 2 is equal to 4 elements, therefore the order of 2 is equal to 4. Generator 3 has 4 elements, therefore the order of 3 is equal to 4. Generator 4 has 2 elements, therefore the order of 4 is equal to 2. Now, let's prove if G is isomorphic to G bar. First, mapping. Define, let phi of 1 is equal to 1, phi of 3 equals to 2, phi of 7 equals 3, and phi of 9 equals 4. Second, 1 to 1. Based on the mapping, it is 1 to 1. Third, onto. Based on the mapping, it is onto. Fourth, operation preserving. The mapping is operation preserving because both operations are the same. Now let's move to the examples and non-examples of isomorphism. Cayley's theorem states that every group is isomorphic to a group of permutations. Every group is isomorphic of a group of permutations. To prove this, that G is an element of G, define a function T sub G from G to G such that T sub G of x equals Gx for all x in G. In other words, multiply each value of G by each value in G on the left. For instance, let's look at U12. We already know U12 equals 1, 5, 7, 11. So, get the product of permutations. T sub 1 of x equals x, and the permutation is 1. T sub 5 of x equals 5x. The permutations are 5 goes to 1 and 11 goes to 7. T sub 7 of x equals 7x. The permutations are 7 goes to 11 and 1 goes to 5. T sub 11 of x equals 11x. The permutations are 11 goes to 7 and 5 goes to 1. Now, here's the Cayley's table of U12 and U12 bar. They have different labels but they are isomorphic. Lastly, here are the properties of isomorphism that concludes our topic for today.